Hey, what's up, everybody? This is Dr. Tracy Tubes for EE135. We're going to be talking about fuel cells today. This is a second part of a three-part series. Excuse me. So last time we talked about a phosphoric acid fuel cell. This time we're going to talk about the solid oxide fuel cell, right? SOFC right here, right? So the idea is, again, fuel cells are all the same, where you put hydrogen comes in, oxygen comes in, water comes out. The only difference here is a membrane and electrolyte itself and the molecules passing through, right? So on the right hand side here, this is kind of a picture of what the fuel cell operates at, right? Before we get to that, let's talk about this solid oxide fuel. What's so special about this, right? So it's a hard ceramic material, something like it says zirconium oxide, right? One of the biggest issues with this type of solid oxide fuel cell is that it's very high temperature, right? Meaning you have to be at this 600 to 1,000 degrees Celsius for it to even start working, right? If you're not going to be at this temperature rating, the ions won't pass through the electrolyte, and you're not going to get any electrical energy out, right? So this alone probably kills it on a lot of smaller application stuff, right? You gotta go to places where temperature is not that big of a deal, right? One other big issue at temperatures is this high is that you will affect the startup time. So because to turn this on, you need to get the fuel cells to 600 degrees Celsius. It requires a lot of external support, meaning you have to somehow you have to get the temperature up to this level for it to even start working. So it takes a long time to get to 600 degrees Celsius. So start time is slow for this type of fuel cell. Naturally, that again limits us on the type of applications we're looking at. You know, something that goes on off pretty quick. It's probably not going to be the best, right? Also, not just start time, but normal operations, right? So changing energy level as well is slow. So if you want to go from one type of energy level to another, meaning you want to change your megawatt output, you got to change the temperature to do that, right? And that, again, that's relatively slow. Why does that matter? Well, that means this type of fuel cell is not good for quick on-demand changes in the power system, right? Remember, loads come and go. You want to count this as one of your base load units, something that we could say is just going to push out 10 megawatts all 24 hours. You don't want this to be the one that turns on, turns off based on the loading, right? So it really kind of narrows it down on the type of applications, right? So pretty much, one good thing about this though, with the high temperature, is much less susceptible to outside influence, right? So it can tolerate impurities pretty well, right? Because at a high temperature, all the impurities that come in probably kind of gets burnt off, so it's not even going to affect us, right? This is good. So then what that means is we don't have to filter the oxygen coming in. Another big thing is, because the temperature is so high, it will kind of, I won't say self-make, but we can use natural gas as the hydrogen, right? You remember natural gas has hydrogen built into it, right? But because we have high temperatures inside the fuel cell, the natural gas coming in will automatically get swapped over to the hydrogen for us. So then we don't have to make the whole hydrogen reformer that we talked about, meaning we don't have to make the hydrogen, right? That we previously had to do in figure 6.48, right? Talking about the reformers and the carbon monoxide output, right? We don't have to do that here. We literally plug in natural gas, and it'll naturally do it. So we kill a whole step in the hydrogen making process. So that's really good because making hydrogen is pretty hard, right? So this is a pretty promising thing in terms of fuel cell, right? We skip a whole entire cycle of the logistics and development of the fuel, right? So with that here, oops, I think I have to do shift tab, yeah. So here, this is ideal for large scale generation for utility, right? And we're going to say in megawatts, right? Meaning this could be like 10 megawatt, 20, 30 megawatt generation. That's okay for a fuel cell, which is really, really big for a fuel cell, right? So this is pretty much utility side stuff, right? Now, how does it actually work? So here, we'll keep it down here, right? Let's talk about an anode first, right? What comes in? We're going to have 2H2, so 2 hydrogen molecules going to come in, right? Here you can see on the anode side, it's much different from the other ones. We're actually receiving 2 oxygens. So the hydrogen comes in here, and the oxygen gets pulled in through the electrolyte to the anode side. So we're actually going to get plus 2 oxygen molecules, right? But they're going to be ions, right? 2 oxygen molecules coming together, they're going to be missing the they're going to have the extra electron, right? We want to get rid of it, right? That's where the 4 electrons here is going to come out. So this is 2O2. I think that's a typo here. It says, this says 2O2 squared. That should probably not be a square. Let me double check. Oh, it is okay. That is supposed to be there. So what that means, I remember now, is this has to be a superscript. Way is you do superscript. What this means is 2 minus is we have 2 electrons extra. That's what that means, right? So we're gonna have 2 oxygen molecules come in, and each molecule is gonna have 2 extra electrons inside it, right? And then that's going to want to go away. And that's where these 4 electrons come in, right? So this needs to be subscript. Sorry. The 2 hydrogen molecules come in. We got 2 oxygen molecules here, right? So I guess there's 4 hydrogen molecules, 2 of 2 sets of each, plus 2 oxygen molecules. This is going to turn into, right? Draw our arrow. Get rid of this guy. This is going to turn into water, right? We got 4 hydrogen molecules, 2 oxygens, so it's going to be 2H2O. Right? Boy, this is a subscript. Script. Oh shoot. Then we're going to add 4 electrons, right? Because that's what came out of this. That's going to be a script for that one. So here, these 2 times 2, these 4 extra electrons get taken out. And this again, what comes out the negative terminal goes to the load. That's our electrical energy. All right. On the cathode side, so let's copy this. Right. The cathode side here, we're actually taking in oxygen, right? So let's get a bunch of this stuff away. So we're putting in oxygen on this side, right? So here, subscript, oxygen. We're also getting in 4 electrons, you can see here. The positive terminal, 4 electrons getting entered. So that's going to be on this side, right? So we're going to have 2 oxygen molecules, 2 of them to be exact, 4 electrons. That's what comes in. What comes out is going to be this guy up here. 2 oxygen ions. Right? Does that make sense? We got 2 oxygens, we got 4 extra electrons, 4 extra electrons latch onto the oxygen molecules. This is what goes through electrolyte. This is this big arrow. So these oxygen ions are going to go through and then recombine with the anode over here, right? So that's where your electrical energy comes in. So remember, at the end of the day, it's still 4 electrons come out for every 2 hydrogen that comes in, and 2 water molecules come out, right? The only difference is that we're using oxygen ions now. Previously, we were using something else, right? So, with that being said, it's just another variation of fuel cells, right? One thing that's really good about this is the efficiency. Efficiency for this fuel cell is high, right? It's about 60%, right? Again, 60% is really good when they talk about raw energy conversion. Right? Remember, a lot of places under 50% for steam generation is pretty normal. So just the fuel cell by itself with no extra add-ons is a 60% efficiency. Not to mention also that it makes its own natural gas. Hydrogen through natural gas. So that's a lot of positives for this type of fuel cell. Again, we could also go combined cycle and get upwards to about 80% efficiency, right? Again, the reason why it's better is 600 degrees, 1,000 degrees is really hot, right? That's a lot of energy to make a lot of steam, a lot of pressure, and turn a big fat turbine with a big generator next to it, right? So, if you could get over this 600, 1,000 degrees Celsius, in which probably a lot of applications can't, but if you could overcome this high temperature thing, everything else seems pretty good about a solid oxide fuel stuff, right? So that pretty much concludes the solid oxide fuel part here. We're going to go ahead and talk about one more after this, and we'll call it a day for our lecture series, right? And just to tell you, this is the second slide in the 3-part series, so we'll probably save this and load up in Moodle as well, okay? So see you guys in a second.